Hello, this is Richard. Today, I would like to introduce our recent paper, Disrupting Model Merge, a parameter level defense without sacrificing accuracy. This paper is accepted by ICCV 2025. So first, let me give some background about the model merging. So recently, a very popular paradigm to train a model is called pre-train fine-tune paradigm. So we first train a powerful base model on night scanner general purpose data, and then fine-tune such model on downstream tasks using domain-specific lessons. One example is that we first pre-train the ResNet 18 on ImageNet, and then we fine-tune such pre-trained model on MNIST so that the fine-tuned model can solve the digital classification problem. And under the pre-trained fine-tune paradigm, model merging has emerged as a promising technique to combine the multiple independently fine-tuned models. So let me using the task arithmetic, a well-known method, a well-known model merging method to explain what is the model. So we define the pre-trained base model with theta play, and the fine-tuned model on two tasks is denoted as theta A and theta B. We define the task weight as tau A equal to theta A minus theta B, theta B equal to theta B minus theta B. So now we have theta A, tau A, tau B, and the model logic is directly to linear combination of these three parameters. So if we want to have a multitask model, then we can directly get theta merge equal to theta plus lambda A times tau A plus lambda B times tau A. Lambda A and lambda B are two scalar and two hyperparameters. For example, lambda A can be 0.5, lambda B can be 0.4. And if we want to forget the knowledge with task A, we can get the theta merge equal to theta A minus lambda A times tau. So we can find actually this process require very little computational cost, since we do not retrain the model. And this is the reason that such technique has attracted the attention of the CV community. But we find there may be some potential risk of the model merging. First, the merged model inherits the specific capability of its source model, and also the model merging changes the parameters so that it blends parameters in a way that makes it difficult to trace the model origins. These two properties enable the free riders to steal the capability from open source models and falsely claim ownership by model merging. Recently, there are some existing work that realize this risk, and they propose a watermarking method to detect the unauthorized model merge after it occurs. However, we think such strategy has some limitations. First, these techniques are inherently passive. They do not prevent merging, actually, and IP violations can still happen before the detection. We think this leaves a critical security gap. There is no defense that proactively blocks the unauthorized model merging into the model lab. So let me using the figure to explain the situation. So let's say the model provider train a model A, and they publish the model A to the internet. Then the other provider can download the model A, and using model merging to combine the model A and the model B, they can have a very strong merge. Such a model can, if this is a classification model, it may have a very good classification accuracy. If it's a generator model, it may generate a very good image. And in this paper, we consider a proactive defense. So it's before publish model A to internet, the model provider can firstly use the proactive defense, transform model A to model A1. The standard allow model, the model A and model A prime before merging, actually they have exactly the same moment. So publish model A or publish model A prime does not affect the purpose of the model provider, so that you can still show your model is good. And then after model A prime is published to the internet, and the writer download the model A prime and using the model module, they can only get a very full model. For example, if we set classification task, they can get accuracy less than 10%. And if it's generator mode, it can only generate loss. To achieve this goal, we first ask why model module works well. The key observation in the paper one is that module works because the model lies in the same or nearby region. So it's a red figure shows. Here we have CWA, and the red part means the loss is low, blue part means the loss is high. So since the theta A and theta B are fine-tuned on the CWA, so they are close to the CWA on the parameter space, and they are located in the same position. Then after the model module, we can find that the theta module also are located in this position, so that the model module, after the model module, the module has a very good performance since they are located in a low loss position. Our idea is that if two models are located in distant positions, merge them would result in performance degradation. So if we can find a way that move theta A to theta A hat, then using model module theta B and theta A hat can result in a very poor performance model. Since it's a figure shows the theta merge hat is in a low loss region. So based on this idea, we propose the parameters. The core idea is to apply the functional equivalent parameter transformations to push the model into a distant position in parameter space. Here, the functional equivalent parameter transformation ensure that the functionality of the model remains unchanged before and after protection prior to the merger. So this design first ensures the performance of the pre-merge mode does not drop, and also ensure that the performance of post-merge mode is balanced. Let me make two examples of this transformation. First is MLP parameter rearrangement. So we met here is a common definition of MLP. So if we can insert a permutation matrix P so that W1 becomes W1 prime, P1 becomes P1 prime, or W2 becomes W2 prime, then this MLP, the parameter change, since the W1 is related to the W2, the W1 prime and W1 is different. The parameter change. But we can find actually your output, your functionality is exactly the same. When our models contain MLP, we can use such transformations to change the parameters. And basically, all models contain the such MLP model, which means such transformation can be widely used. A second transformation is called random multi-head scaling. So given a multi-head attention modular defined in here, this is a well-known definitions. So we can randomly generate two non-singular and symmetric metrics A and B, and then we can modify the parameters of 2, 3, 3, and W. And we can find by such transformations, actually, the output, the functionality of this whole attention module can change. And the thing is, attention module is also widely used in modern machine learning models. Such transformation can also apply to most of models. So this transformation also preserves the functionality and largely modify the model parameters. By applying such transformations, we can obtain the models that's different in parameter space, but the functionality is exactly the same. So let me show some experimental results. So here, the UMP means unmerged model without protection. UMP plus means unmerged model with the protection. Since we do not change the functionality, we can say actually they have exactly the same accuracy. But we can say the MMP minus means the merged model without protection, and the MMP plus means the merged model with protection. We can see the blue bar and the red bar is merged model without protection. They can achieve very good accuracy close to original, and the IP violation happens. And we can see that for the green and the yellow bar, since with the protection, the accuracy drop is a lot. So the provider can only pick a very poor version. Hence, we protect IP. This is also hold for the image generation task. We can say for MMP minus, the merged model without protection, the provider can still generate a very good images. But the merged model with protection, we can say the provider can only generate noise. So in the conclusion, in this paper, we present a proactive defense from the kernels against the model motion protection fine-tune the model's capability from being inherited by the provider. And in the future, so we next plan to apply the kernels in the physical medicine. That's all. Thanks for listening.